Good afternoon, Professor.
Good afternoon, Caroline. Well said. And good afternoon, Felix. Felix says good afternoon to Caroline and to Christina. And Felix says hello to everybody. Wow. Okay. Felix says hello. Felix is in the back. Felix of Fortnite fame is in the background saying hello to Alicia, to Amanda, to Christina, to Amy, to Kimberly, to Jamalette, to Kevin, to Amy, Amy K. I should do that more. And Caroline wins a triple award for video and hello and tolerance and smile. Oh, I'm not okay. I don't want to call attention to, but smiles. Wow, even in physics. Okay, awesome. I appreciate it. There should be a. Okay. Anyway, hello everybody. Who did I not say hello to? I think that. Oh, that is a small class, maybe. And hello, Savannah. Oh, wait, I didn't say hello to Savannah.
Good afternoon, Professor.
Good afternoon, Savannah. Awesome. All right. I feel terrible. How did I think because I always assumed that I said hello. All right. That was terrible. Terrible. All right. Yes. Good afternoon, Savannah. Good afternoon. But I think that's everyone. Blah, 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 blah. Okay. Okay. We'll just get rolling. Right. Yes. We will just get rolling. Here, what we're going to start now. Again, I kept, at the beginning of the semester, no, more people come. Just kidding. Hold on. Here we go. I can never, the waiting. Okay. I think, all right. Oh God, good afternoon, David K. Awesome. Oh, more people coming. Also, I just realized how deformed that dude looks in the bottom right of my picture. Ugh. Professor Walter pointed out that it always looks deformed and gross, and he's right. Huh. Okay. Good afternoon, David K. Okay. Good afternoon, anybody that I missed. We're going to start. Well, to cut to the chase, we're start more and more. The assumption is, as we progress in physics 203 and then physics 204, more and more the assumption is we've laid down these fundamentals in such hopefully depth, or at least such expansion, that more and more the idea is that we have the fundamentals at our disposal to be able to make quicker and quicker leaps and bounds through applications. So and maybe that will excite some of you more. In some ways, some of this will start going a little bit faster and a little bit faster, etc. And some way to stress some of you, I don't know, but always you can text and email, etc., etc. But here's something I'm getting at is, the last 2 days or so, the last day, we added two-dimensional displacement vectors so that we could have the technique forever of adding multidimensional vectors of any kind. Okay, now we're going to go to the next stage, possibly the more interesting stage, velocity vectors. More people coming in, sorry. Oh, and good afternoon. No problem, but thank you and good afternoon. I still don't know I can't say it because it's a private. There's a number. And good afternoon, Felicia. Awesome. Okay, what I'm saying is this. We're going to get to addition and subtraction of velocity vectors today. It's the exact same compute. This is a good example. What we're going to do today is a good example of the relationship between, or the distinction between, physics and math. Because what we're going to do today, or start today, is the addition or subtraction of two-dimensional velocity vectors. Now, you're going to see, hopefully, that the mathematical computational procedure for that is precisely identical to the computational procedure for adding displacements. Like, the math is the same, but what it means physically is different, and different enough that how you set up the problem, or to be more concrete, how you know whether the problem is, in fact, an addition problem or a subtraction problem, requires that you understand the physical concept that's going on. So what we're going to do today, hopefully you'll see that the math is the same, but you also want to see that the physics is different. And you can only get these problems right if you first and last think about the physical implications. So it's a good example too, where a lot of people will say, okay, I know how to do the physics, I just never know how to start. But once I start, I know how to do it. Today is kind of, hopefully you'll see that the physics is knowing how to start. And the way to know how to start these computations is to think about physics. All right, anyway, now, when I'm saying that we're going to start accelerating a little bit also here, what I mean is the problem. So, okay, so we're going to go over velocity vector addition. The way to do it is the same mathematical procedure as yesterday, as 2 days ago, hence the sine squared theta plus cosine squared theta equals 1. You know, that's a reminder that anytime I ever write that, what that means is everything you know about right triangle applies. That's a shorthand. That's a clever way of writing Pythagorean theorem and SOHCAHTOA in one statement. That's what that's supposed to mean. That trig identity means SOHCAHTOA applies and Pythagorean theorem applies. So that's the math, and that's always true of any kind of higher dimensional vector combination that we're doing. We're always thinking about right triangles. But the top statement you might on board right now, you might recognize as the fourth form of Galileo's principle of relativity, right? It came up after the train of thought problem. It all homework. It all seemed maybe abstract at the time. It's really going to start finding its application today. What it says in English, well, I'll get into that in a minute. But anyway, so we're going to have to use that physical concept, Galileo's principle of relativity, plus the mathematical computations of right triangles in order to add two-dimensional velocity vectors. Now, that's what we're about to do. Now, where am I going to get the example problem from? Okay, that's where the acceleration of the course comes into play. The example problem I'm going to do on the next page is taken from the homework that you're currently doing, or that was just handed in today in principle, I think. Yeah. It was a big packet of homework that I gave you, very big. It was meant to be as much an instruction manual of walking through exercises and concepts as it was example practice. It was both. I'm going to skip directly today. I'm going to go over a problem in that packet that's way not at the beginning. Okay. It's at the heart of the packet. It's on page. So whether you've done this or not, as usual, I think you'll benefit from this. You'll benefit more if you have tried it, obviously, but you should tune in either way. On page 5 of homework 7, it's a part of the whole packet that's called space relations part 2. Of that, it is subpart Roman numeral 1. Of that, it is section B. I just came in. Yeah. Okay. Sorry. Okay. It's a problem that it's part of the packet that's about addition of 2D velocity vectors. Now, I'm skipping all the way to that now because, you know, we're starting to move along in the semester. All the problems that lead up to this are meant to help you lead up to this. And some of them are very similar to what we did in class on Monday. They're different versions of that. If anything I do today confuses you, or if anything I do today confuses you or goes too fast or whatever, I highly recommend that you go back and look at the packet and look at the stuff leading up to it. As I say, it's a very long packet, partly because it's meant to be an instruction manual as much as it is practice. But if all that stuff is trivial or obvious to you, or you did it in high school, or just is self-evident, good, fine. But the point of all of it is to lead essentially to this. So I'm going to go straight to this right now. Again, I think it'll be more exciting and interesting and informative to follow if you've tried it, but I definitely think it's worth tuning in either way. So the problem that I'm turning to is the problem about the Pontiac and the Toyota. I have it on my screen. It's hard to switch back and forth between screens. I hope you have it in front. Just raise your hand. Raise your hand if you have this packet in front of you, and so whether you did it or not. Just raise your Okay, cool. So I'm saying, I keep them up for a second. Just raise your hand if you have this packet in front of you. If you know where I am, I'm not asking if you did it. Great. Oh, that's a lot. Okay, great. Awesome. Okay. All right. So we're turning to that. Thank you, guys. I'm not. Okay, I see almost all of you, so I'm not even going to name you by name. Okay, so it's the Pontiac Toyota problem. Again, this is a problem in adding or subtracting velocity vectors in 2 dimensions. It is based on adding vectors in general, which we first learned with displacement vectors in the beginning of the packet and on Monday, and based on the concept of the relational quality of velocities. All right, so here's a situation, and you could put your hand down now. Thank you. All right. So the situation is the Pontiac Toyota problem. It's a classic problem. This is not a joke problem, I don't think. Anyway, it's the Pontiac Toyota problem. So you're given some information about two cars. I'm diving right in and saying, okay, you're giving this Pontiac, you're giving this Toyota, and you're giving a fact about a gas station. There's three objects being referred to here. So let's name them right away. I'm letting P stand for the Pontiac. I'm letting T stand for the Toyota. I'm letting G stand for the gas station. What I'm told is the velocity of the Pontiac relative to the Toyota is 30 miles. Someone else is here. Sorry. Okay. I'm told that the Pontiac is driving at a velocity. That means speed and direction, right? A velocity of 30 miles per hour, okay, in a direction of 30 degrees northeast, right? So we're now in two dimensions, but we're given a velocity. And the velocity, we're given a velocity of the Pontiac. But remember, we're recognizing, as we're going to explicitly recognize them, we're recognizing that all velocities are truly relations between pairs of objects. There's no such thing in physics as a velocity of a single object just in space. This is the whole recognition that the Earth moves, right? I mean, it all goes back. Oh, sorry. Oh, no problem. Thank you. No. Got it. Oh, good. No, that's important. Thank you for got it. Direct chat person, of whom there's only one. Okay, so remember, from here on in, if I ever walk up to you and say, how fast is that thing going? You always have the right and the responsibility in physics to say, how fast is it going compared to what, yo? Like, right? Because there's no such thing as just going fast. There's going fast compared to something. And depending on what you're comparing to, your answer will be different. And as long as you're comparing to an unaccelerated object, all answers are equally valid, right? This is the point of like the Earth is going 65,000 miles per hour compared to the sun, but it's going 0 compared to itself, and it's going 650,000 miles per hour relative to the center of the galaxy, and all of those numbers are equally correct, right? So this Pontiac is going, and now we're going to take that concept of the relational quality of velocities, and we're going to apply it to two dimensions of space. So it gets a little intricate now. We've got a Pontiac that's going 30 miles per hour at 30 degrees northeast, from the frame of reference, from the perspective, from the coordinate system of some Toyota. So I say V, so you see my drawing at the lower left. I'm not computing anything. I'm just depicting what's going on. This is my DFP, my diagram, step one. I've got a vector that represents what the Pontiac is doing as measured by, as observed by some Toyota. That is what VPT means, velocity of Pontiac relative Toyota. And let me reinforce that what that really explicitly means is that is what would be seen, measured, observed, scientifically accurately, taken in by some Toyota that regarded itself as stationary. Right? This is from the perspective of a Toyota. This is like in video games and stuff like that, what they call point of view, right? And please understand, just like video games, like, so that arrow to the left, that arrow to the left that says 30 miles per hour, 30 degrees, that's the arrow that the Toyota would see. And that's the arrow that the Toyota would see, and not just see, I don't mean like in a dream, I mean like accurately measure with whatever equipment you could imagine. That's what the Toyota would see, what's happening from its point of view. If the Toyota, so this is, I always get confused in video games, but I think this is what they call like first person view in video games, right? I mean, I actually get confused about that, but so this is what the Toyota would see if the world is moving past the Toyota and the Toyota is just there in the center of the screen, viewing itself as at rest, right? But then the next arrow is what a gas station sees the Toyota doing, right? So then now the next arrow is a different velocity, but it's literally not just a different velocity. It's a velocity from a different frame of reference, right? The next arrow says VTG. It's what the Toyota is doing relative to some gas station. So if the gas station is now the frame of reference, if a gas station regards itself as at rest and watches the world, it's seeing the Toyota go by at 60 miles per hour at 30 degrees, at 20 degrees southeast. These numbers, by the way, are somewhat, unfortunately, somewhat similar to the very numbers we did yesterday. Well, I don't know if that's unfortunate or not, but it is a coincidence that these numbers and these directions are very similar to the ones we did on Monday. Maybe that's good, but it is just a coincidence. So we've got two different velocities here that we're going to try to relate to each other, but please understand that they are not just two different numbers or two different observations. They're observations made in two different reference frames. Okay, if anybody were to ever ask, if you were to ever, and people do this all the time, sometimes consciously, sometimes unconsciously, if you were to back up and say, okay, I get it, the Averbaum, like I get, that's what the Pontiac's doing according to the Toyota, and that's what the Toyota's doing according to the gas station. But like, if you were to then say, okay, but like, what are they actually doing? Or if you were to say, okay, but what's the gas station actually doing? Like, I understand if the gas station views itself as at rest, it sees the Toyota doing this. If the Toyota views itself as at rest, it sees the Pontiac doing that. But you might be tempted to say, okay, but like, what are they actually? I mean, that's if they view themselves as at rest, but what are they actually doing? Or you might say, okay, but which one of them is actually at rest? Like, or you might say, wait, is the gas station attached to Earth? Like, is the gas station the one that's like truly at rest? And it's just which you might picture. And I have to say, there's no truly at rest. Like, none of these is truly doing anything. It's just the gas station regards itself as at rest. The Toyota views itself as at rest. Actually, for that matter, the Pontiac views itself as at rest too, as well. They're all doing different things, but they're all viewing them just like a video game. Okay. The deal is, though, that we're saying, just like my son is playing Fortnite. Are you in point of view? Are you in it's first person, right? Like, yes. Yes, okay. He says yes, and I believe him because he knows. So yeah, like, and the point is, in the world of that game, that is true, right? But here's what we're saying in physics is those games work for a reason. They're not wrong. And there's no world that's more right than any other world. Like, it's all video games is what we're saying. The Pontiac is playing a video game. The Toyota is playing a video game. The gas station's playing a video game. And not one of them is more correct than any other. Honestly, I'm saying this to everybody, including myself. Like, and you might even say, okay, but really, dude, like, come on, I've got to picture this. I don't want chaos. Like, what's really going on? Like, you could say, yeah, I mean, I'm sure the gas station is attached to the ground. I'm not trying to fool you. The gas station's attached to the ground. Some Toyota's going past it and some Pontiac's going past that. But the gas station, that doesn't mean that the gas station is more objectively stationary than the other two, because yes, the gas station's attached to the ground. And what's the ground doing? The ground is attached to the Earth, and the Earth is hurtling past the sun at 65,000 miles an hour. And then even there, if you want to say, okay, so then that's the reality. I say, well, no, but the sun is going past the center of the galaxy at 650,000 miles an hour, right? So this is actually a very deep idea. It really is. And it goes on like that. Anyway, I don't want to get myself, but we're taking this. And by the way, you wouldn't be scientists. You wouldn't be in this class if at some point in your life, you didn't sort of flirt with this notion on your own and kind of maybe, I bet there are some of you in the class that have sort of thought of this on your own, maybe when you were playing a video game or something. Or maybe some moment when you woke up in a car on the highway and then you didn't know if the car next to you was going forward or you were going backwards, train of thought. I bet there are some of you in the class that have had this thought in your mind at one point, thought about it for a minute, maybe you had fun with it, maybe you got yourself confused by it, whatever, and then thought also, okay, well, that's interesting, but that's just me being weird. Like, that's just like weirdness or fun. What I'm saying is it's real science. You're not alone. You're not the only one who's ever thought about this. This is a real thing. And we take it so seriously in physics that, in fact, there comes a point where this is what all leads to Einstein and everything else about the universe. Like, comes a point at which we all take this so seriously that some people can't even believe how seriously we take it. Okay. Anyway, saying, we got these two velocities, the velocity of the Pontiac relative to Toyota, the velocity of the Toyota relative to the gas station. Neither one is more correct or anything like that. But now, what's our question? Well, in the homework packet, they ask a lot of questions. They ask you to do a lot of diagrams. I mean, you should do that for practice, blah, blah, blah. But right now, what I want to get, I'm going to sort of skip around it. Okay. I'm just doing a holistic. I think the ultimate, well, you might want to write this down before I turn the page. I think the ultimate question, the most straightforward question I could ask here ultimately is, what is the Pontiac doing relative to the gas station, right? That would be the most straightforward question I could ask. I mean, but I could ask a bunch. I mean, for that matter, I could ask, what's the gas station doing relative to the Pontiac? And all those could be answered. But I think the ultimate question, I'm writing this down, the ultimate question, what is the velocity of Pontiac, or sorry, is it Pontiac? Yeah, Pontiac relative to gas station. Like, which just means exactly what it sounds like. If you're in the gas station, and I shouldn't even say in, I don't even care if you're literally in the gas station, but if you're at rest relative to the gas station, if you are in the same frame of reference as the gas station, which could mean that you're miles down the road. And in this case, probably just means you're somewhere on Earth. As long as you are in some perspective, as long as you are going at a velocity, which is the same as the gas station, so that you constantly have the gas station in your field of view, right? If you are in the same frame of reference of the gas station, what we ultimately want to know is, what would you observe the Pontiac to be doing? What, and by we mean what speed and what direction?
Yeah, I got 163 kills.
Nice. Wait, do I like it? My son just got 163 kills, which proves he knows physics. Nice. So I want to ultimately know what's the velocity of the Pontiac relative to the gas station. So, but bot kill. Wait, are they bot kills? Or I mean, wait, are they against other actual players, or are they against actual players? Okay, okay. Wait, so someone wants to know, wait, someone's really paying attention. They want to know, literally in this one game, you just, hold on. Yeah, they're challenging this. How did you get 163 in this game that you're playing right now, or overtime? Like
overtime. Well, in this game.
You literally got 163 in this game since we've been starting.
I'm playing 1v1s and I'm killing by.
Oh, he's doing 1v1s. He's doing, no, he's doing 1v1s. He's doing.
Are bad.
Okay. No. Okay. All right. They get it. We all get it. All right. Well, I appreciate the honest exchange here. All right. Everybody's, yeah. Okay. Okay. He's tied for first. Okay. Yeah, no, fair enough. I appreciate you guys really do pay attention. Wow. Nicholas is okay. And Samuel. All right. Very okay. All right. And yes, he's 8. And yes, I let him play Fortnite. That's a whole other discussion. Okay. Don't tell his mother. Okay. All right. So our ultimate question is what's a Pontiac doing relative to the gas station? Now, how do I know what to do? Like, hopefully you understand physically, and I might stop in a second. I think that's a reasonable question, right? I mean, and I know the homework is asking to draw a million different diagrams, and they're all useful. Okay, they are. I don't want to get into all the diagrams right now, but they are very important practice, and we'll at some point, or I'll post something or something. I want to get into a couple of the diagrams right now. But I hope it's clear that would be a question physically. I mean, if A sees B doing this and B sees C doing that, what is A see C doing, right? Oh, and now that I put it that way, maybe that's a hint as to how we figured this out. The whole idea here, like, all right, so let me even try to be really clear. Hold on a second. Like, I say this right here with step 1 DFP, right? This is a diagram and facts of basically what's going on here. And I'm sort of summarizing and distilling this very involved problem from a very involved packet. But I'm saying basically step 1, the diagram fact pattern is that you've got these 2 velocity vectors that were given, these 3 objects that were labeled. And I'm saying step 2, at least what I'm extracting from the problem right now. So this is kind of like classroom version of homework problem. I'm saying step 2, what is the question? I'm saying the question is, what is the velocity of the Pontiac relative to the gas station? And that means, what is the speed and direction? Now I'm going to say step 3 before I go any further, like as far as how would I even figure that out? Step 3, the GDP, the general definition and principle, is Galileo's principle of relativity, specifically form number 4. The first mathematical, computational, seemingly practically useful version we see of the principle of relativity is that thing that I've written before, but we've never really used yet. Like I say this, given any 3 objects, or let me be even more specific, given any 3 constant velocity objects, or in other words, 3 distinct frames of reference, let them be called A, B, and C. So given any 3 objects known as A, B, and C, 3 objects that are going with 3 distinct velocities, each of which is constant. So 3 different perspectives on the universe. In other words, 3 equally legitimate perspectives on the universe. Given any 3, what we have said is that their velocities relate to each other in a certain way. They relate to each other in this way, the thing that was written on the front of the notes today. The velocity of A relative to C equals necessarily the velocity of A relative to B plus the velocity of B relative to C. I know this just looks like the property of transitivity or something like that, but we're saying something, I mean, and it is in a way, but we're saying something about velocities when we say this. And just note again, this is a GDP. This is a general statement of truth that is real and important in physics, even before we start this particular problem. That is one of the reasons that I'm writing it with A, B's, and C's, even though I'm well aware that in the problem, I already defined objects to be called P, T, and G. But I'm trying to emphasize here that this is for any 3 objects at all. As long as they're each moving at constant velocities, this is how the 3 objects' motions relate to each other, right? So this is Galileo's principle of relativity, form number 4, and it refers to it a lot, you know, throughout the homework. That's in general. That's in general how velocities work. Now, I'm going to remind you, when we first saw this in the train of thought idea. We first saw this in a one-dimensional context, in a slightly more straightforward context where it's kind of easier to picture and easier to believe. And I'm going to remind you what it means in that context. But then what we're saying now, the sort of unexpected cool thing of physics is, once you believe in a concept in one simple coordinate system, it's still true even in complicated multi-dimensional higher speed coordinate systems. I mean, so there's always the idea of physics is we come to an idea that we really all believe, even as non-physicists, that's simple and self-evident about the world around us. And then what the physics does is to say, let's take that idea really seriously. Physics is not supposed to be new ideas. It's supposed to be old, familiar, acceptable ideas applied super seriously and super consistently and super quantitatively to then conclude things about the world that we didn't know before. So what this is saying right here, if you just have random objects A, B, and C in general, and you just have one dimension, say A is U, and say B is the subway, and say C is the subway station, or A is U and B is the escalator and C is the subway station, just whatever. Then what we're saying is the velocity of U relative to the subway plus the velocity of the subway relative to the station equals the velocity of U relative to the station. And that's why you take subways, right? In other words, you sit in the subway and you're going 0 miles per hour relative to the subway. So you're just like chilling, eating your sandwich. You're going 0 relative to the subway, but the subway is going 60 miles an hour relative to the station or relative to the New York City streets, all of which are attached, right? Like, or relative to Earth, if you want to say. So therefore 0 plus 60 equals 60. You end up going 60 miles an hour relative to the station or the streets or New York or whatever. And that's not because of gasoline. That's the nature of velocities, right? And you also know, and you could take, that that's so true that then if you start walking down, like now put yourself instead of on the subway, instead of in the train, say you're on the escalator in Columbus Circle or whatever, you know that it doesn't only, like, it's easiest to see that that's true when zeros are involved. But then people tend to think it has something to do with gas. But even when zeros are not involved, it's true, right? Like, you know that if someone's standing, if there's a ramp that's going up the Columbus Circle station, and the ramp, I mean, not a ramp, an escalator, and the escalator is going like 20 miles per hour relative to the station up. And you know that if you walk up the ramp at now he's up to 184 kills. I'm just saying. Okay. If you go, yes. Okay. If you go up the ramp at 2 miles an hour relative to the ramp, and the ramp is going up 20 miles an hour relative to the station, then you know you're going 22 miles an hour relative to the station. How do you know that? Because you pass people on the ramp. Right? Like that's why you do that when you're in a rush, because you believe that your velocities add together. You don't believe they're redundant. You don't believe that your two just gets absorbed by the escalators or something like that. You believe you can accomplish something by putting together the escalator speed with your speed. And you also know that if you walk backwards, if you go opposite to the subway, then it's like a negative sign. I mean, it is a negative sign. And you even know, if you're small enough, or like Felix used to do this, and his brother Jesse, you know that if you go to an up, I'm saying that you, once upon a time, used to like to walk up the down escalator, like in the Barnes and Nobles in Brooklyn, right? You would walk up. Okay, who says he doesn't now? Right. So even now, and so do I secretly. So it's fun to go up the down escalator in Barnes and Nobles. And if if you do it exactly right, and if the up, I mean, if the escalator is going down at 20 miles an hour relative to Barnes and Nobles, and you go up, you go the opposite direction at 20 miles an hour relative to the escalator, you can look like the Roadrunner cartoon or whatever, like flailing your arms and legs and all that. But someone watching you from the bookstore sees you just like flailing but staying still relative to the bookstore, right? Okay, everybody knows this. What they don't know is that it's really as true as it looks. It really is that true that velocities add in that way, even including negative signs. One last thing, and then I'm going to apply to this. Just notice, so we're on part of what I'm just saying is, hey, velocities add. Like, and we all knew that, but like, we didn't know that we knew it necessarily. Or maybe we did. Velocities add, but I'm also saying that, but when you add velocities, you have to add the right velocities. They don't add, they only add because velocity is a relation. And you have to properly, in a proper sequence, incorporate their relational character in order to add them. Let me say again, velocity of me relative to the escalator plus velocity of escalator relative to bookstore equals velocity of me relative to bookstore. That's what the A, B, and C sequence is saying up here. Like, it's very specific. It's to plus, it's to A plus A to E equals to E. You know what I'm saying? Like, you can't scramble around the letters. That's what it means to add. So for example, if I throw a tennis ball across the room, across my face, so the tennis ball has a velocity relative to my face, but then at the same time, if someone else in this room were to throw a basketball across my face, like, so tennis ball relative to room, and then you also have basketball relative to room, you can't add those velocities together. That doesn't mean anything, right? Like, you have to be careful about your frames of reference and organize them correctly if you're going to add velocities together. Well, I'm going to take the risk. Well, okay. What happens though? What do you do if someone's throwing a basketball across a room and someone, or whatever, observing a basketball having a velocity relative to the room, but then there's also this tennis ball having a velocity relative to the room? Like, do those relate at all in any way? Well, yeah, if we actually believe, they relate in a different way. If we actually believe in math, and we believe that math applies to physics, then, and if we actually believe that this statement that I just wrote here as a GDP, if we believe that is true in general, not just for some particular problem, then it also follows it's a statement of math. You can do math on it. You can subtract, for example, the BC from both sides, and then say velocity of A relative to C minus velocity of B relative to C equals velocity of A relative to B. What I'm really trying to say is we add velocities that are in different frames of reference, different perspectives, but we subtract
10 more kills until 200.
10 more kills until 200. Okay, for anybody who is paying attention at home. I'm proud. I'm pretty, 9, excuse me. Okay, we subtract. So we add velocities from different frames. We subtract velocities from same frame. That's an important, this is all just contained in the statement we're making. And again, let me just remind you, all of this is just physics expanding and expanding and expanding and expanding all of what it really means to believe that the earth could possibly move and yet we don't feel it. That's what all of physics is. It gets into everything in the universe, but it all starts with the earth moves. But 9 more kills. We subtract velocities from 8, excuse me. We subtract velocities from same frame. So quickly on this, just want to, and then we're going, okay, 7. Okay, hang on, 7. Okay, 6. Okay, 6. Okay, hold on. We're going to apply this now to this problem. But what I'm trying to say right now, I'm trying to say a general truth that I think is easiest to picture and 5 and compute in 1 dimension. It's easiest to picture, possibly believe. Okay, 4. Okay, one second, but awesome. This is easiest, I think, to believe, to picture, and even to compute in your head in 1 dimension. What we're about to do is take this concept, if we're actually buying it, and apply it to 2 dimensions. So the mathematical details will be that much more detailed. Like we're going to get numbers that I don't think I could just do in my head, but hopefully I could believe in my head. What I want to say here though is, but everything I say right now about 1 dimension carries over to 2 dimensions or 3 dimensions. But one of the things I'm saying that I want to carry over is if I subtract from both sides, like basically I'm saying this: if I know the velocity of me relative to the subway station, and I know the velocity of the escalator relative to the subway station. So I know the velocity of me relative to the subway station, and I'm booking up that escalator. And I know the velocity of a person who just standing on the escalator. Let me say it again. If I know the velocity of me relative to the subway station, and I know the velocity of some escalator some escalator person just, and I know the velocity of that person relative to the subway station. 200 kills, Mazel tov, congratulations, well done. Okay, I'm not at all distracted, I assure you. Very good. 200 kills in 4 days. And by the way, if you're frustrated right now, you're saying, could Yagram stay on the topic, please? Well, okay, I agree, but also just remember, I said everything in physics comes from Galileo. And Galileo, remember, is the one that teaches us the sun is the center of the universe. You know what I'm saying? You know what I'm saying? Okay. That's my defense. Sun is this. Get it? Sun. Okay. Anyway. So if I know the velocity of me relative to the subway station, and I know the velocity of a ramp stander relative to the subway station, then if you think about it, say I'm going 22 relative to the subway station. Just okay. Hold on. Congratulations. Yes. Well done. Look over there. Look at your. Okay, and then come back. Okay. Don't wake anybody up. Okay. Sorry. If I'm going to, we will do this. I promise. If I'm going 22 relative to the subway station, and you're standing on the ramp, and you're going 20 relative to the subway station, then it's intuitive that I'm going 2 faster than you, right? From your perspective, I'm going 2. What did we just do? We subtracted, right? It's like, hopefully, if you think what I just said is like obvious and like, why am I wasting your time? Because what I'm trying to do always in physics, I'm trying to point out the obvious and then say, now take that, it's obvious, but it's not obvious that it's important. That when you say my velocity relative to the subway station is 22, and your velocity relative to the subway station is 20, then my velocity relative to you is 2. I just subtracted. See, so when you're relating velocities that are both in the same frame of reference, you subtract. When you're relating velocities from different frames of reference, you add. That's what this statement is trying to say. And the bottom line, and now we're going to turn to the problem. I promise. Of course, my son will walk right back in. But what I'm really trying to say to anybody who's still paying attention is it's this concept that tells you from now on, if you get a word problem, if you get a complicated problem involving velocities, as this Pontiac Toyota problem is, if you're ever trying to figure out whether you're going to add vectors, place them tip to tail, or subtract vectors, the way you figure out whether it's an addition problem or a subtraction problem is by looking at the physics and the reference frames like this. So I'm ultimately saying that Monday you learned how to add vectors at tip to tail and do the math, make an XY chart and then add up the numbers. And if you were subtracting vectors, you'd put them tail to tail and you'd make an XY chart and you'd subtract the numbers. That's the math. That math is never going to change. But which one to do, whether to set it up as addition or subtraction, that's what you could only know. That's what you need to decide about velocities. And that's what you could only know given what frames of references are given or not. Okay, so we're now going to turn to this problem. We got this Pontiac, we got this Toyota, we got this gas station. We're told what the Pontiac is doing relative to the gas. So here. So now I'm going to here in this problem. So now I'm going to step 4, PAW, right? I'm doing the particular application in work. Step 4, PAW. So here in this problem, like A is P, B is T, and C is G. You know what I'm saying? And I'm not doing that to confuse you. I'm trying to make a point that A, B, and C are general objects that have to be in that sequence. But here what we have are specifically Pontiac, Toyota, and gas station. So here in this problem, I would say, look over there, prize. No, on the table.
Why did you get this?
You don't want it? Okay. Well, I got it for you. You deserve it. But now I have to teach. Oh, sorry. Okay, so let's be okay. So we have to. Okay. So,
Thanks,
sorry.
Grandpa.
Okay. So here in this problem.
I don't deserve this.
That's very nice of you to say. Yes, you do.
Tell your chat that I just got like a $50 present.
Okay. But they'll, okay. I'm just making sure that I give the right Pontiac. Did I give the right letters? Yeah, Pontiac, Toyota. Yeah. Okay.
Yes. Relax. Dad, I put
Hey,
a comfy.
Awesome. But wait,
$20 card.
wait. Oh, I love that's awesome. I do need to teach now, but I'm psyched. I love Comfy. Wait, what did I just do? Oh yeah, okay.
Why?
Okay, Felix.
I got Radiance, Gardevoir, and Cresselia. That's sick.
Wait here, sorry, I'm getting myself confused. Okay. trying to step. So this GPR form number 4 that we're now going to use is a statement that is so general and so true and so mathematically true that it can be rearranged to whatever you're looking for. Okay. And you're going to see that as we practice other problems. Like it's up to you. It's up to us to rearrange it to solve for the thing that we're solving for. Okay. But yes, look at the purple thing, but I need to teach right now. So here in this problem, we're going to solve for velocity of the Pontiac relative to the gas station. In order to get that, we're going to add together the velocity of the Pontiac relative to the Toyota plus the Toyota relative to the gas. Now, honestly, the thing that even though I just spent, as usual, 15 minutes talking about the abstract general principle, honestly, I think that's the hardest part of all of this. I think that's where, that's the physics. If you get the physics of what I'm saying, and you get that therefore, that the physics of what I'm saying is that this statement, this seeming law of transitivity thing here, that it's true, and it's true. The part that's true is that pattern of frames of reference, that A to B plus B to C must equal A to C. But once you write that down and you substitute in the letters that apply to the particular problem, you arrange it any way you want to solve for anything you want. Oh, I should also say, in fact, before I go any further, let me say 2 other implications of this, of GPR4. Well, wait, yeah, no, I better. The expanded, oh, there's something in the chat. That's actually awesome. Okay. Excellent. I'm psyched to hear you say that. Okay. And someone in the class just voted that you should get a Zoom account so you can literally join this class from Zoom. And I think we should think about that. I think that's very sweet that someone just said that. Okay. I just got a shout out that I'm amazing. Oh, to that person. Oh, so that person, the direct chat person, is amazing for advocating that. Okay. All right. Expanded version of this. Expanded version of GPR4. Remember, GPR4 is our first mathematical application of this idea that velocities are relations. So to break it down into smaller steps for a moment that we'll use, again, all this might be self-evident to some of you. Any of you who's ever really contemplated the idea that you don't know whether you're moving or not, and I'm telling you, you're right to have contemplated that. You probably thought about all of this in some way or another. You just didn't necessarily know that what you were thinking about was rigorous physics. So here's a rigorous way to put it. What GPR really says is if you only have one object A, then the velocity of it relative to itself is necessarily always 0. Again, that's the video game point, right? If you're in first person, you are never going at any speed relative to you. You always see your own nose, or you always see your own gun or whatever, right? I mean, but that's true. You, in your frame of reference, you are stationary if you're always. So if anybody ever asks, how fast is that thing going? And then you go, relative to what? And they go, no, not relative to nothing. Just like, how fast is it going? Well, the answer is 0 if you don't compare it to something else. But then it follows from that. Say you have 2 objects, object A and object B. The velocity of one relative to the other is always necessarily the exact opposite, the exact negative, the exact reverse of the velocity of the other relative to the one. If the Earth is going 65,000 miles an hour to the west, past the sun, then the sun, to the east past the sun, then the sun is going 65,000 miles an hour to the west past the Earth. Thank you very much. I appreciate it. Thank you. Okay. This video is sponsored by Dad, right? Right. So if you have one object, it's always going 0 relative to itself. If you have 2 objects, then their velocities are necessarily always symmetric mirror images of each other. Even if they're in multi-dimensions, even if it means flipping a full vector arrow, right? In other words, the velocity of me, if I'm going 30 miles per hour at 30 degrees northeast relative to you, then you are going 30 miles per hour, 30 degrees southwest relative to me. Just flip the vector entirely, right? That's if there's two objects. And then if there's three objects, then we're now saying, well, then you really got to do math. And the velocity of one relative to the second is the second relative to the third. The one relative to two plus two relative to three equals one relative to three. Okay, this is the expanded version of all of this. So you can rearrange these statements any way you want, make whatever substitutions to solve for what you want. But I'm telling you right now, this is what you need to set up the velocity vector combination problems. Now, with all that buildup, with only 25 minutes left, let's actually do it to this Pontiac Toyota problem. I'm going to tell you right now with one last stall that this is one of those rare times where I actually, this front loading that I'm doing, this over talking about all the physics before I actually do the computation, honestly, even if I know it frustrates some of you and I do sympathize with that, honestly, it is necessary, because once I do the computation, you're going to be like, oh yeah. The computation is just like what we did Monday. And honestly, if you've ever been that person ever in your life who's like, I can do it once we're doing it, but I never quite know how to do it on my own, whatever it is, or I never quite know how to start, but once I start, then I know what to do. Right. Then I'm telling you, right, you're not alone. The difficulty of physics is how to start any, okay. But yet he usually wins nonetheless. So here we go. Okay. So here we go with the Pontiac and the Toyota. What I just did in my physics is I just established to myself that what I need, if I want to solve for the Pontiac relative to the gas station, what I literally need to do is add. All of this was to decide whether to add or subtract. But I just came to the conclusion, and whether to flip any of the vectors or anything. I've just decided that all I have to do is, we're going to do just like yesterday. We're going to go, that's a little. Very much the numbers again, sort of sadly, very much like yesterday. So this diagram, okay, this diagram right here of these two vectors being placed tip to tail is now the problem that we're trying to solve. We're literally going to add these two vectors, and we're going to get the third, the triangle completion vector, the red vector. Whatever we get for the length, whatever we get for the length of that is the magnitude of our final answer of velocity. Whatever we get for the angle of that is the direction of our final velocity. So, and we're going to do the same method as Monday, but just now understand what we're doing now is we're not adding, these don't represent distances anymore. These represent rates of motion. In other words, each one of these vectors is long or short because it represents something that's going fast or slow at a moment. These vectors each represent something that's happening like right at their tail, if that makes it like the long vector, the 60 miles per hour vector, means that if the car is right at the tail of that vector, that at that moment it's going that fast and in that direction. Hang on, and in that direction. So these now are these are long lengths that are meant to represent things happening at points. That's a little bit more abstract. Pardon me. Yes, but I've got it. Yes. Why?
Because you're not saying that I'm cool.
You're very cool. I've been saying it all. You're super cool, but now it would be really cool if you would let me also teach. Okay. Thank you. Yeah, no, the class heard how cool you totally are. You're way cooler than I ever was at age 8, 16. I never won Fortnite Battle Royale when I was 8. Okay, but now I've got to teach, as was our, okay, he's too cool. Okay, all right. They just said you're too cool. So they totally agree. Shout out to everybody. Okay, all right, so here we go. So what am I going to do? even though this means something different, I'm going to do the exact same thing I did Monday. Thank God, because we only have 21 minutes. I'm going to zoom in on each vector individually. I'm going to break each two-dimensional vector into its one-dimensional components, right? So zoom in. So now we're still in PAW, step 4, practical application work. Zoom in and separate each velocity vector into its components. Because now we're believing we're applying GPR form number 5, and I see this thing in the chat. I'll get to it in 1 second. We're saying again, each two-dimensional phenomenon is really two one-dimensional phenomenons occurring independently yet simultaneously. We said it about displacements on Monday. Now we're saying it's just as true of velocities. It will ultimately be true of accelerations, forces, electromagnetic fields, whatever. If it's true, it's true. But wait, something's in the chat, so we're gonna do it. You're very kind, and you're both very kind, and yeah, I think you're being very kind, but thank you. Okay, so I'm gonna zoom in on the next page. It's tell me if you need me to go back. So I'm zooming in on the first. This is a zoom in. Zoom in on VPT. VPT was 30 mile. Anyway, 30 miles an hour at 30 degrees northeast. So what do I say? I say that's really some amount east plus some amount north. Now, technically, of course, you could also say that it's some amount north plus some amount east, but my technique, my strategy to all of you for all time, for all vectors is whenever you're dividing a vector into its tip to tail components that are being added, always draw horizontal first. That is not a law. That is a strategy, but it's always the right strategy. Do include your tips and tails, and this is what you practice. This is the thing I could have gone up and then over, and that would have seemed right, and it would have seemed okay, and then it would get me all fouled up. So please do practice this. But I go over and I make a tip, and then from that tip, I start a tail and I go up. So I'm saying northeast is really some combination of east plus north. And what do I mean by that? I mean specifically, this side is going to be 30 cosine 30, and this side is going to be 30 sine. Like I'm starting to get used to this and skip some steps here, right? I'm saying for all time, the adjacent side will be hypotenuse times cosine of the angle. The opposite side will for all time be the hypotenuse times the sine of the angle. So this one is 15, and this one is 0.866 times 3. So that's like 20. I think it's 24.7 or something. The 25 point. All right. So now notice, right? So I just got the sides of this triangle. Now notice this triangle is a vector triangle. It's a velocity vector triangle. So please, this is where this becomes physics now. Like I just did some math on a hypotenuse to get some legs, but those legs are not spaces. The arrows on my piece of paper have length, but the length represents motion in the actual world. In other words, this 15 that I just got means 15 miles per hour. This 26 that I just got means 26 miles per hour. What we're saying here in this triangle is that if at some moment you're instantaneously going 30 miles per hour at 30 degrees to the northeast, that is equivalent to at that moment going 26 miles per hour to the east. I'm totally going to look at that chat. This looks great. Whatever's in the chat looks awesome. I'll finish the sentence and I'll totally get it. But I'm saying if you're going 30 miles per hour at that angle, that's equivalent to going 26 miles per hour approximately to the east, while at the same time going 15 miles per hour to the north. We're talking about what's happening at an instant here. These are rates of motion. And yes, that means if we did it for a full hour, we would get 30 miles that direction which we could have accomplished by first going 26 miles in that direction and then 15 miles in that direction. But these are rates of velocity, not displacements. Now we're in the chat. I know it was a great chat question in your chat. Hold on. Yeah. So this is, wait, hold on. Yes, right. This is space relations part 2, question 2. Yeah, I know it's like a million subparts in that. It's space relations part 2. Yes. Yes, but you please, but yes, delighted. Let me teach. So yes, it's space relations part 2. It is question, space relations part 2. And then it's question. It's really, sorry, it's question Roman numeral 1. Wait, it's space relations part. Well, honestly, what it is page 5. I believe you said that. It's question Roman numeral 1, where it says relative velocity vectors in depth, and then part B of that, capital letter B, relative velocities in 2D. Hold on. I'm going to ask the person, but it's worth asking because I know this whole homework thing is like really thick and long. And also, I just, wait. And also, I'm distilling. Oh, you do see. Okay. Oh, good. Right. And it's, thank you, Felicia. Right. And it's little Roman numeral 1. Well, no. Wait. Okay. Wait. So I'm glad direct chat person is clear now, but I understand why they're asking. And I appreciate what Felicia's putting in the chat, but wait, hold on. But partly what's unclear is I'm taking the whole situation and actually I'm distilling it down and asking, if anything, what I'm really working out right now, to be honest, what I'm really working out is part little Rome. All right, I'm going to switch screens for a second, just so you can see. I know when your phone for a minute. Hold on, let me switch screens so you can see what I'm doing. Okay, but Felix, please. Yes, it's okay.
You can't.
Okay, just so you can see. Because I do appreciate what the person's asking, and I appreciate what Felicia just said. But honestly, I'm sort of zooming out on the whole question and getting to the heart of the matter. And I'm like skipping a lot of the mini questions. So if this is what we're looking at right here, this, what's on your screen right now, this relative velocities in 2D, if that's what we're looking at, and I'm skipping a lot of the drawings and stuff like that, maybe to catch myself up, where what Felicia just pointed out, where it says little Roman numeral I, what is the velocity of the Toyota relative to the Pontiac? Okay, I'll tell you the answer to that. The answer to that is 30 miles per hour at 30 degrees southwest. Okay, that I can do in my head. And you can write that down. I don't have to put a ton of work into get that. Is kind of what I was saying 10 minutes ago. Like, velocity of me relative to you is the opposite of the velocity of you relative to me. So we were told in the problem what the Pontiac is doing, and maybe I should have just done that first. But we were told what the Pontiac is doing relative to the Toyota. So if you flip that, you get what the Toyota is doing relative to the Pontiac, right? And the answer to, I'm going to check in with all of you in a second. We're still going to finish this, but I don't want to lose anybody. So if you're following me now, if you're looking on the screen, like little Roman numeral I, the answer to that is 30 miles per hour at 30 degrees southwest. Because what the Pontiac is doing relative to the Toyota is 30 degrees northeast. So what the Toyota is doing relative to the Pontiac is the opposite of that, the negative of that, the inverse, the mirror image of that, 30 degrees southwest. Similarly, and I'm going to check in to make sure you're with me in 1 second, but similarly, little Roman numeral II, what's the velocity of the Toyota relative to the Toyota? The answer to that is 0. Okay, I think can you just put thumbs up if you're with me, if you know where I am on the sheet and you know what I'm saying? Can you guys put thumbs up? Thank you, Caroline. Okay, awesome. Wait, who else? Oh, and they're in the chat. Okay. Makes it. Okay, cool. Yeah, Felicia. Yeah, because VAA equals 0. Right. Okay, cool. And thank you, Savannah. And thank you. And I can't see you all right now because I'm actually looking at the sheet too. But yes, thank you, Amy C. Yes, relative to, right. Okay. So now what I'm saying is, because I know now what I'm trying to answer, honestly, if anything, I'm trying to actually skip straight to 3C in a way. I'm not doing all the, well, I mean, I guess I'm doing 3, A, B, and C. I've just drawn some arrows And the red arrow that I just drew on my page, when I go back to that screen share, like I've drawn arrows to represent the different velocities. And the red arrow on my page is is D, what the Pontiac is doing relative to the gas station. The red arrow on my page is the thing that is unknown in this problem right now. I mean, there's a lot of things that were unknown, but it's the thing that's unknown that actually takes work to get. There are a couple of the questions we just answered, like Roman numeral little I and Roman numeral little I, like those were unknown, but we could sort of get them in our head by just saying, okay, VAA equals 0 always, and VAB equals negative VBA always. But now to get the real missing piece of what does the gas station see this Pontiac doing, that's the red arrow in my picture that you can't see for the moment. And that's where I'm going to put all my computations to solving for. But I'm very glad you stopped me to ask where we are. Is everybody sort of clear where we are? Because we've got 10 minutes and that is just enough for me to get, okay. That is just enough for me to actually get an answer to this problem. Okay, cool. Okay, thank you, Felicia, and thank you, everybody. All right, so now I'm going to stop that share and go back to what I'm doing. And I will go a little fast, but again, okay, cool. And thank you, Caroline. But the fact that you guys just asked me that too kind of confirms, I mean, and it makes me feel a little bit better. Yeah, you can't see, you'll see in a second, but I only have 10 minutes, so you got to bear with me for a second. Hopefully you'll see, if you're with me now, if we're all oriented the same way, then you'll see the computation I'm about to do is not the hard part and never will be for you. The hard part is knowing how to set up the computation and all that, which is what everything we've just been talking about. So, I mean, I think that was valuable. So, okay, now I'm going to go back to computation and I am going to finish it by cracky in the next 9 minutes. Okay, I'm stopping that share. Okay, I'm going back to this share. It's all about sharing. Okay. So I've just zoomed in on the velocity of the Pontiac relative to Toyota. Now I'm going to zoom in somewhat quickly. I'm going to zoom in on the other one. Now I'm zooming in on VTG, the velocity of the Toyota relative to the gas station. So it's a longer vector, right? It's like 60 miles an hour rather than 30. And it's a less steep angle. It's 20 degrees from its own little reference eastern axis, right? So it's not 20 degrees from the other one, it's 20 degrees from the eastern axis. So this is VTG. So I zoom in on this and I say, okay, something that's going southeast is really going some amount east, 60 cosine 20, and why cosine? Because it's adjacent to the 20-degree angle, and it's going south at 60 sine 20, and unfortunately 20 is like an annoying angle that I have to do on my calculator. So I say, so this is like 20 point, Felix, please, we're almost done. And this is 56 points. So I'm just doing this on my calculator and I'm in degree mode. Okay. And these two numbers, 56.4 and 20.5, are miles per hour. So now what do I do with all these miles per hour with 8 minutes left? Now I'm literally just going to add them together. Okay, but Felix, please. Okay. That's yes. Okay. I love you. Okay. And they love you too, but they will hate me if we don't finish this problem in 8 minutes, 7 minutes. It's like the equivalent of 200 kills, 8 minutes. So now what am I going to do with all these? I'm literally going to add them together because velocities add. And we all now believe that velocities add, but we only can sort of picture it and believe it in one dimension at a time, like the escalator ramp at Columbus Circle. So that's what we do to this. I'm just going to divide this into two independent yet simultaneous worlds, one dimension each. In other words, I'm going to make an XY chart just like I did yesterday. Only the X's and Y's now are velocity in the X direction and velocity in the Y direction. And I'm literally going to say, okay, in the X direction, I was going 15 miles per hour. Oops, sorry. Hold on. 6 minutes left. Okay. Vx, Vy, and what is this? This is velocity of Pontiac relative to train, velocity of train relative to train. So Vx for the Pontiac was 15 relative to the Toyota. And for the Toyota, relative to the gas station was 56.4. And VY for the Pontiac was, sorry, no, it was 26. I'm sorry. VX was 26. Okay. Right. And VY was 15.0. But for the Toyota was 20.5, but south negative, so 20.5, right? And then, so just like yesterday, now I'm going to add these numbers up, even though they're velocities, because velocities do add. So I get 82.4, and I get negative 5.5. And so what do I do with that with 6 minutes left? Just like yesterday, I say, okay, so at the end of the day, what the gas station sees is a Pontiac that's going 82.4 miles per hour to the east, while it goes 5.5 miles per hour to the south. So what the gas station sees is that the Pontiac does something like this. And notice I drew my horizontal first. I draw the horizontal from a tail all the way to a tip, and it's going literally to the right because that's a positive number, right? So the horizontal VPG equals 82.4 miles per hour to the east. But from the tip of that, vector, that long vector, I draw the tail of a short vector that goes down because of the negative, or south because of the negative sign, and it's 5.5 miles per hour, right? So I draw horizontal, and then from its tip, I draw a tail of vertical, and then it makes it very clear that my final answer is this hypotenuse pointing at an angle I will, but at an angle that is, I know I've done this, I know I've set this up right for two reasons. One, my final hypotenuse here that I'm about to get and will be done is more or less looking like my original red line in my original triangle, my prediction that I get a long line that was pointing somehow to the southeast. That's what I've got here. So that's good. Also notice that the angle that I'm about to solve for is between the two tails and yet measured from the horizontal. So the angle is like south of east. That means I'm doing something right. Like it makes sense to me. And that's why I always draw the horizontal first and then the vertical from that. So my final answer, my final speed of Pontiac relative to gas station is, well, it is the square root of the sum of the squares, right? Is the square root of 82.4 squared plus 5.5 squared. And I don't have to worry about the negative signs or anything because they get squared away. So like 82.6. Right. That's, I guess that's funny, actually. Okay. Hold on. I will, but okay, wait, but I've got to finish this. So that's the speed is approximately 82.6. That's the square root of the squares. Sorry. Oh, yeah. And the angle I'm running out of room. I'll put it up here if you don't mind. The angle is the approximately, because we're already rounding off to just the arc tangent of 5.5 over 82.4. And again, I have to pay attention to my negative signs, but I don't have to put them in anything because the negative sign means south or west or whatever. And that's what I'm going to say at the end. In other words, the angle, and then we're done with 2 minutes left. The angle is the arc tan of 5.5 divided by 82.4. So like a very, very small angle, that makes sense. 3.81 degrees. And I look at my picture and I can see that it is southeast. So I apologize that this is so sloppy, but I'm saying this is part of the answer right here. And this is part, the answer is a speed and a direction. Together they make a velocity. The final velocity, so this is what the gas, and I see I have 1.5 minutes left. What the gas station observes is that a Pontiac is going 82.6 miles per hour at 3.81 degrees southeast, like almost, it's almost due east, but whatever. That's what the gas station sees. The Pontiac sees itself going 0. The Toyota sees the Pontiac doing 30 miles per hour. The gas station sees the Pontiac doing 86 miles per hour. Which one of them is right? None of them. All of them equally. None of them equally, right? But this is, and if I were to now ask, with 1 minute left, if I were to ask, okay, how fast is the gas? If I were to ask, what's the velocity of the gas station relative to the Pontiac? The answer would be 82.6 miles per hour at 3.81 degrees northwest. If you follow that, you definitely follow all of this, right? Like this, what here is in yellow on the page is what the Pontiac is doing from the perspective of the gas station. What is the gas station doing from the perspective of the Pontiac? The exact opposite, right? That's the idea. So that's it. That's one. So you guys have been very attentive. You're all heroes. And my son has Darth Vader's lightsaber, and that's the real punchline of today. So I'll hang up for a second for their questions, but you guys are awesome, and I'll see you next week. And I'll post a practice exam tomorrow night. Practice. You don't hand it in. You just use it for practice, and you bring in questions on Monday. Okay, you guys have been very, very. Thank you.
Bye, Professor. See you next week.
Thank you, Professor. Have a great day.
See you never.
Darth Maul's like.
Have a good day, Professor.
Have a good day.
Have a good day, guys. Thank you. Oh, wow. Bye. Thank you guys for being so flexible and patient and loving. And okay. Oh,
I love
okay. Are you good, Chloe? Or do you have a question? Are you good, Chloe? Or I can stop.
Yeah, I have a question.
Oh, yeah. Okay. Let me stop recording. Hold on.